Wait,
Come on.
stop.
We're live. It says you are live. Hi,
Can
everyone.
you undo live? Or does, yeah, I guess that just, we end when we live. How are you doing, Ben?
Well, how are you, more to the point? Last
I
time we
am
were on,
healthier.
you had COVID.
I had COVID. I am better. When we interviewed Matt Liberty with the Oscilloscope, I told Matt it's probably the only time he'll be interviewed by somebody that knowingly has COVID. So, hey, Mike, how are you?
Hey, Bill, how you doing? Hey, Ben.
Good.
Hey, Mike.
Good.
Good to see you. Thanks for jumping on today.
Absolutely. Yeah.
So Mike was, if for those that don't know, we have Coriolis-effect.com is our website where you can join our Discord. And Mike has been not blowing up, but he's been posting to our Discord this week. And we're going to talk about that. He found some things interesting with some arbitrary waveform generators. So we'll talk about that. We can talk about test jigs today, but Ben, you've got a loaner toy behind you. Is that right?
Yeah. And it just arrived basically yesterday, so I haven't had a chance to learn how to drive yet. But this is the beautiful and extremely luxurious. This is like this is the Rolls Royce of oscilloscopes here, right? The MXR series, MXR 608A by Keysight. These are the ones you see at DesignCon at the Keysight booth showing DDR5 and even whatever is the cutting edge technology, you know, eye diagrams with PAM4 and PAM6 and all sorts of crazy signal integrity stuff, because this thing has 8 channels at 6 gigahertz. So I could choose to buy one of these if I didn't have a house.
Right.
Did it come with probes?
It came with probes. The probes themselves are probably, you know, thousands of dollars each.
Right.
This is a beautiful machine, but like I said, I've had 0 hours with it yet to drive it. So I'm thinking next week we stream and do a little demo of this beautiful thing while I've got it, because I have to send it back to Keysight. This is a demo loaner. But,
now, do you have enough stuff to do an eye diagram, do you think?
I don't have the kind of signal generator I should probably have. I'm hoping this has something built in that will do it. It doesn't have that on the front panel, but on the side panel, there's a bunch of additional generator, like it has generation. So if we look at the side here, you can tell like the basis of this is actually an ATX motherboard. Right. So that's what gives you the beautiful user interface, is software running on essentially a PC inside this thing.
Right.
And that's coupled with all their very special silicon to get that bandwidth and sampling on the front end. But all of these, there's a row of BNCs with different options here, and there's a generator output right here at the top.
Wow.
So I'm assuming there's some capability with that, although it's not one of the fancy gold-plated N types you get with the high-end RF gear, but still, I believe there'll be some cool stuff I can do just with what's built into this and the software running on it.
Very cool. Very cool.
So we'll take a look at that next week.
Yeah, we're getting comment. Oh, here, let me just throw one of the comments up here. Yeah, it's very sexy.
Yeah, isn't it? Yeah, maybe it's more like a Ferrari, except it's big and heavy. That's why I picked Rolls Royce. It's absolute luxury and expense, but it's not like lean, mean sports.
Right.
And expense. What would that be in oscilloscope? What would a Ferrari be in oscilloscope form, Mike? Something small, light, and really fast.
Yeah.
And just as expensive.
Well, my concern when I see something like that and then the ATX board, I'm thinking to myself, that'll be what breaks in 6 years. It'll be the most expensive PC break that you've ever owned. You know, if you owned one of these, you'd have to get the $140,000 machine service because a $1,000 ATX board broke.
It's possible, but if it's anything like everything that Keysight does, you know, I've heard this phrase from one of the famous self-help authors out there, but he has this phrase: "How you do anything is how you do everything," and that's why brands like Keysight and Tektronix and Rohde and Schwartz and LaCroix all have reputations for excellence. I believe unless you dropped it, something like that will work.
Right.
50 years from now.
Right.
Some of the custom silicon might degrade because, that's high value, low production run stuff.
Right.
To be cutting edge enough to measure the cutting edge silicon. The silicon that's measuring the cutting edge silicon is even more cutting edge, and that means
But
it might suffer from things like electro migration.
Yeah. But if the cutting edge silicon breaks on my $140,000 analyzer, to me, that's a fair cop, right? It's like, oh, of course, the expensive thing broke. I just don't want the keyboard connector.
Right. It's just annoying when it's something that should be cheap and easy.
Right.
I get you.
So we just got an interesting comment here, and this is something Mike and I have been talking about all week, is measuring stuff. Mike, and we've been talking about the difference between test equipment as the standard for engineers when you're working versus test equipment that it's like, I need what I can afford, right? Because I can't afford personally test equipment. The companies I work for can. I can afford to rent test equipment. I can afford to buy old test equipment behind me. But, so what about the new test equipment? And the answer is, well, your mileage may vary, right? Is that kind of what we found this week, Mike?
Yeah, I was messing around with a lower end affordable signal generator, and I've never had access to a higher end one, and so it's that you're in that position where you only have what you have, and that's what you know, and you need multiple ones to compare to know the limitations, and even then you still don't know everything,
right? So, Mike, you looked at a DG1022Z or Z.
Yeah, that's a nice Rigol
Ben would
signal
say.
generator. Yeah,
right. And I was looking at buying one. I was looking at buying yours, maybe. And then you compared it. I shouldn't say compared it, but at the same time, you looked at an Agilent what?
Oh, it's a 33500B series. It's their normal. Actually, it's the same thing as the Keysight. It's just rebranded, or it's the older one, but it's the same model they're selling now under the Keysight brand. 33500B. Yeah.
And the difference is the Rigol is a new one for you. It's you bought that new, right?
Yes, brand new a few years ago. Yeah.
Right. And
like $500 for it, and now it's like $350.
Right.
Brand new. Yeah.
And the Keysight is thousands of dollars new, but you bought yours used.
I did. Yeah.
So we were comparing them this week, and I didn't expect there to be a difference, but you found a couple differences in the waveform generators right off the bat. What was the first thing you found with the Rigol that you and I went, whoa?
So the first thing I've always seen ringing on the output of the square waves.
Right.
And that's what I've been focusing on most. I guess ever since I did a 555, I've been in search of the perfect square wave, right? It doesn't exist. But but the Rigol has ringing on the square waves that I assumed is always. I guess that's to
termination
normal.
Or something. Yeah.
Yeah, and I don't know the cause of it, if it's internal to it or if it's just inductance in the lines or whatnot, but it's always been there. And I felt, and that was the first thing I noticed when I got this Agilent was it doesn't have this ringing, basically it goes up and I could actually show you, I have it on the scope now and I could show you the difference just for what the ringing looks like. Let's see.
So, so it's important to notice that you didn't get the ringing all the time. Go ahead, Ben.
No, I was just going to ask, explain your test setup for this, because did you use terminations, 50 ohm cables?
Yes, definitely.
And do the generators have terminated outputs as well? In other words, they're
my understanding is that they have 50 ohm terminated outputs. Yeah,
right.
So even
Okay.
if you don't have the other end terminated, it'll reflect back and get absorbed.
And we did a test of that, and we'll talk about that. But I had him remove his termination because I was going to have him change it to 60 and then 40 in case it was a mismatch. But the ringing just scaled right with everything. It's like baked into the signal ringing.
Yep. So it really is part of the generation.
Right. So yeah, show us on your
Okay, so I just switched cameras.
Yep.
So this is the scope, and it is terminated. I have the 50 ohm terminators turned on it, and the top one is the Rigol, and it's you have to be fair about this. That ringing only really is that prominent when you're sweeping the square wave. That's one thing I discovered. If you don't sweep it, you get some ringing, but not that much. And then the bottom one is the Agilent, and it's both of these are singles. The oscilloscope is stopped right now, and it's
right.
They were basically sweeping. If I turn it back on so it's running, I don't know how to get it to trigger on both at the same time. But that's the Rigol that's being triggered right now at the top. And then if I switch it to the bottom, or if I switch it to the other channel and trigger on that, you can see that the Agilent looks nice and smooth, right?
That's
compared
superior,
to
for sure.
And I've never seen that before. I was like, oh wow,
Right.
And so it to me must have, and I think this was discussed a bit in the Discord, but I didn't read it thoroughly. Something to do with the way they're actually generating it.
Yeah, let me turn off the sweeping on the Rigol. I'll just turn that off, and let me reduce the frequency because this is at 15 megahertz. I'll maybe do it 5 megahertz.
So both of these generators are good for like 30 megahertz or thereabouts.
Yeah, the Rigol goes up to 25 and the Agilent goes up to 30. Yeah, they're in the same class roughly in terms of that spec. Let me make the Rigol or the Agilent also go at 5 megahertz.
So, somebody just asked about understanding why a sine wave is not square, and there is a whole thing to discuss in there. Hang on, let me change the camera just a second. A square wave is sine waves in my book. It's just certain sine waves added together. And so we use a square wave to determine how well it behaves for sine waves.
John Scarfone asked a good question. Is the top trace on a bandwidth limited mode? That's actually bit me in the butt in a testing project.
Is it in bandwidth
where I did all these measurements and then someone said, "Did you check the bandwidth of that channel?"
Right, right. I don't even know if the Rigol has that
on the wrong setting.
Right. So Mike was saying he doesn't know if the Rigol has a bandwidth limit, but I know my
but on the scope that we're looking at.
Oh, the scope is full bandwidth. It's a 1 gigahertz scope, and it's not bandwidth limited in the scope.
It's probably a menu option.
So do you want me to turn on bandwidth limiting?
No. It's just like
no.
You didn't turn it on. In other words,
was asking if it was on.
Right.
Yeah. You said no. So
this is what it normally looks like. This is what I'm used to seeing out of the Rigol in terms of its ringing. Let me set the duty cycle back to 50 as well. 50%.
So I wonder if one of them just has a really really dense frequency domain, like Fourier synthesizer to generate it. Like I would imagine that might be the case for the Keysight, where they do the signal generation in the frequency domain,
right?
With a Fourier synthesizer that has a lot of points, but then the Rigol maybe does it just using a time domain circuit. If I want a square wave, normally I don't care that much about ringing, and that's probably the attitude of the designers. It's like, it's tolerable because people are looking for a rising edge and a falling edge, not utter perfection. Because again, when I'm designing something and I want a square wave, normally it's a clock for something. So I'm not that fussed about it. But I think some of the people on the Discord chat were discussing it from the frequency domain. Frank Buss had this whole blog post.
He asked about a phase accumulator. Yeah.
Because if you're generating a square wave for audio synthesis, for making music, then having those additional artifacts actually might be objectionable.
Yeah.
The
I do not like ringing on. See, and I'm the opposite there, Ben. If I had grabbed a scope off my bench to make a square wave and it had 5% baked in it, I'd be like, whoa, what's going on here? Because that is the requirement for a square wave, is to transition to that top voltage and critically dampen, if not overshoot it all or anything.
Yeah, well, because you want to make sure you've got good signal integrity, right?
Right.
So
it's an indication of
that
signal
makes sense
integrity.
too. Like if you're doing time domain reflectometry, you need a very good square wave, even
Right.
if it's at a low frequency, but the edges have to be really, really good with no ringing, so that you can accurately do TDR kind of work with it.
So somebody asked here again, I'm going to try this one more time. It's basically a sine wave interpreted. No, a sine wave would be exactly round. It's sine function, not round, excuse me. But if you add the third harmonic, so if you had a kilohertz, the 3 kilohertz, 6, the next one above that, and you keep adding them together, that'll sharpen that rising edge. And so it's the frequency content. If it's the right mixture of odd, you can't add evens, they cancel, odd harmonics that trail off at just the right formula, you'll get a square wave. So you can describe, and that's what fast Fourier transforms do, is they'll take a signal and break it back down into sine waves. And correct me if I'm get that wrong, guys.
Well, Fourier was the mathematician that worked out that everything in the universe is basically
bunch of sine waves.
Not everything, but almost everything.
Yeah.
Can be explained mathematically as the sum of different sine waves of amplitudes and phases added together. And 3 Blue 1 Brown did a really marvelous animated video of that, showing you can even draw pictures with sine waves added together.
Right.
So one thing I would like to say about the Keysight is that if you look at their literature, they talk about this true form technology, which is like a trade secret of theirs. And they compare it to Rigol, which is using DDS, direct digital synthesis. And there's some interesting interviews that Dave Jones did with John Kinney from Keysight. And John Kinney was given a little history of the true form technology, and it came out of their RF group. Evidently, their signal generator group was talking to the RF guys over lunch one day, and they're like, "What? That's what you're doing?" And they basically took that and moved it from one part of the company over to the other, evidently. And interesting, but it's a trade secret. They won't talk about what it's really doing.
I wonder what that is.
Yeah.
So you found a second issue then on your scope. I could see it because I knew it was there.
All right.
When you're back at your square waves.
So let me go back to square waves. Yeah. Let's see frequency. Let's see.
And you were sweeping the top one.
Yeah. So that was the thing that I noticed was like extra ringing. Let me turn the sweep back on. Where'd it go? Sweep. Okay. Do you see the difference there? I can turn off this Agilent. We'll just look at the top one for now. So there's a decent amount of ringing there, right? And if I turn off the sweep, it goes away.
Yeah. Yeah, it's pretty.
So we're wondering, my question was, is it possible that this is a DDS, a list recording of how to make a waveform, and it's baked into the signal that they recorded? In other words, is this a software problem?
It could be. Or the other thing I was thinking is they're switching between two different methods of generation. For the swept one, because it's swept, maybe they are using maybe they're using a superposition based DDS algorithm, and for the other one they might just be using a clock that's divided.
Yeah.
So now watch the falling edge there. We can see that, right? That falling edge where I see 2 at a time. That's not the webcast doing that. That's actually happening.
Okay, so let me increase the sweep, the frequencies involved. It's going from 2 to 5 megahertz right now.
All right.
To better illustrate what Bill is pointing out, I'm going to change the sweep to go from, let's see, start at 5 megahertz and stop at, I think, like 20 megahertz. Did I do that right? Oh, I'm in the wrong mode. Let's see. Stop at 20 megahertz. All right. And let me see if I can get this. Let me zoom in. There, you can more readily see it. Let's see, right around there. Maybe if I single stop it. Let's see. If I do a single shot of it. or actually I can't single shot it to show you this. You have to actually have it running. But what Bill was pointing out is if you look at the falling edge, if you look carefully, you'll catch that there's more of them, more than one.
It's like jitter.
Yeah, and what I did was I took it and I put it into a counter that can measure the pulse width of the positive pulse width, and I found that there's actually more than one pulse width. So it's not necessarily the frequencies that are messed up; it's the pulse widths that are.
Right.
Bill suggested maybe it's dithering,
or should be dithered.
Yeah, it's trying. And if I show you the Agilent, let me turn that back on.
So it's like it's catching a clock edge sometimes and not. And this is the heart of Mike's and my conversation this week. Mm-hmm. Is like when I'm using test equipment, when should I be able to trust the test equipment, or when is the test equipment part of the variables I'm trying to solve for?
So let's see. Let me turn on the sweep on the bottom one. So just for comparison, that's the Agilent doing the same kind of sweep. And you might think that you're seeing multiple there, but I think that's the scope just being slow.
Yeah.
And this was more easy to see on an analog scope actually, because there's no refresh rate on the screen to worry about.
Right.
So on an analog scope, you see that the bottom one is nice and smooth and just kind of goes across, and there's only one pulse width.
Right. So at the end of the week, after Mike's doing all these experiments, I'm like, Mike, I don't want to buy your Rigol anymore. I think I want to buy a used Agilent Keysight or something. That's not fair. If I had my choice, if I didn't have a choice, or if I wasn't going to use sweep mode, the Rigol's probably fine for most of what I want to do.
You and I both said like we're all glad that the Rigol exists, right? Because
That's right.
I wouldn't like say, hey, this thing is crap. It shouldn't exist in the world. No, it should exist.
Right.
It's very inexpensive. Come on, $350 is a lot of money even for that thing. When I was brand new getting into this stuff, I had a hard time paying like $100 for a power supply. I had to justify that to myself, So it's like these cheaper gear is like the gateway drug into all this kind of stuff, right?
Right. And the power supply is so non-sexy, but yet so important that most people end up buying a power supply twice in their lives. Their starter supply, and then their one that'll last them a while. So so we were looking at the right. So then you and I start talking about what are some ways we can generate arbitrary waveforms. Mm-hmm. And so I pulled my AD2, my Analog Discovery 2 out.
Okay, yeah.
And that will do arbitrary waveforms. And Frank Buss on our Discord channel reminded us of that you can run a list. But what's just as interesting, you can run math formulas. Again, it's a PC interface. This uses your computer as a computer. It's got a USB cord and a lead set normally. And you can describe a sine wave as a function of a sine wave in the arbitrary waveform generator.
And as a matter of fact, I would suggest, like we were talking about cheap gateway drugs to get newcomers into the mix. That thing is perfect because it does so much stuff.
So many things. Yeah.
And it's limited in its bandwidth. Like you can only, if you try to make square waves up around 5 megahertz with that thing, it'll look like, you'll see the RC content.
They look like shark fins.
Yeah, shark fins. That's a good.
Yeah.
But down around kilohertz, it looks perfect. It's great.
So, and Mike and I have run into that where we're comparing results. We both have AD2s, and we'll both set up the same experiment since it can act as stimulus and recorder, or scope and everything. And then I'll have to remember, oh crap, we're out of the bandwidth of this thing. I wish it was a 1 gigahertz piece of equipment. Yeah, but it's 100 megahertz, I think. So. Yeah. So then I looked around for another arbitrary waveform generator, and mine is built into my Tektronix scope, I never remember it, MDO3104, but my MD 3000 won't do sweeps. So I have an arbitrary waveform generator that won't do sweeping.
Okay. Yeah.
So I don't really count it, but it's great for built-in, programmable duty cycle, rectangular waves, stuff like that. It does that very well. And then here's my, let me see if I can show it. Here's my arbitrary waveform generator that I've used most of my life. And I just love this thing. Hang on, let me see if I can make it bigger here.
3314A.
Yeah. And it's
Nice,
noisy.
yeah.
It doesn't have an Ethernet jack on it. And yet this thing just has been my arbitrary waveform generator of choice. And I can do a burst number of cycles. Back in the 60s, back in the 80s, 86, I used one of these to create the ultrasonic burst that we ended up using on the backup indicator on today's cars, the ultrasonic thing. So this was my ultrasonic source back in the old days.
Very cool. That's a nice piece of equipment, that one.
Yeah.
And so, but you say arbitrary, but that one would allow you to enter points and create your own waveform?
You're right about that, Mike. This
Not
is
completely arbitrary. Yeah.
a function generator that, because I could do burst cycles, I considered an arbitrary. But you're right. There's no way to get the points into that. So it didn't exist back then.
And I think I have one that's slightly newer than Bill's. This one here. This is a 8165A from HP.
All right.
And it's basically like the one you just described, Bill, but it adds like GPIB on the back, and you could drive it and program it.
But yeah.
Okay, you could do that with yours too. Okay.
Yeah. So you did a bunch with GPIB. You grabbed one. I've lost mine, my little yellow GPIB adapter, but you pumped yours right into Python and never looked back, Mike.
So for that, for those who don't know, what is GPIB? GPIB, General Purpose Interface Bus, but it used to be, it was started just with HP, correct? There's HPIB.
HPIB?
Right.
Yeah, okay, yeah.
And isn't it really an IEEE 488 style bus that it's got other names that can apply to it?
It ended up being standardized as IEEE 488.
Yeah, yeah.
But people call that GPIB. It's like calling Ethernet IEEE 802.11.
Yeah.
Right. So yes, it is 488, and I have always wanted to play with it and never had the time or made it a priority. So Mike, give us a rundown on what you've done.
Oh, so I have the same yellow thing that Bill has.
What is that?
Do you have yours handy?
Oh,
I know, man. I'm putting you on the spot there.
The name starts with a P. Is it a Prologix or something like that, or something? But it's basically it's a GPIB to USB adapter.
Right, which is basically a fancy parallel port, because I think GPIB is 8-bit bidirectional parallel bus with handshaking, and PCs back in the day ended up standardizing on Centronics, but the Centronics printer port wasn't bidirectional at first. It was 8 bits PC to printer only,
right?
With some weird handshaking signals. The printer could send some data back to the PC.
Paper, something like that.
Yeah, but just for basic problem reporting. So it only had really 4 bits of return data. So it was definitely not useful for automating instruments. And so HP came up with they're like, well, we want factories to be able to hook up a bunch of our instruments onto a bus and have a computer controlling all the instruments to automate the final test of the production run. So every board goes into a jig, gets pressed down on the bed of nails, pogo pins, and a user hits a big red button, and all the HP instruments generate the signals and measure the results, and then correlate that and say, yes, this is a pass or a fail. So my understanding is HPIB was invented for all that kind of thing, but you could probably do a lot more with it, like customize what the instrument's doing, right?
So my experience so far has been, I would use Python to just mess around a little bit to drive instruments. And, it's probably the best solution that you have in terms of if you were going to pick a language to do this stuff in. But for me, it was kind of finicky. Like I would come back to it later on, and something would be broken with.
I had that problem too.
And I'm a software developer at heart, so I'm really careful about that kind of stuff. But it would still break on me. So I was watching Curious Mark, and he has one of these old HP 85s, which is basically a basic computer that has a GPIB card you can slap into it, almost like a Commodore PET, right? You could just
right,
and that thing freaking works. you like, and mostly like all this skippy stuff that you're doing with GPIB is all a lot of string-based stuff anyway. You're just cobbling together string-based commands and having it get numbers back and whatnot. And typically the programs you're writing, at least for me, they're little simple things. Like, for example, one to like make your SMU discharge a battery and measure the ESR. You know, you can imagine that's like a 15-line program that would loop around and do that and like change things. And so it's like these programs aren't that complicated. So for me, using BASIC on an old BASIC computer is fine. You know, you don't need like modern computing capabilities. Python is great, but these programs can be nice and small.
And the HP,
I think.
Go ahead.
Yeah, I was going to say, I think HP must have like sold that as a whole system to companies like Texas Instruments, National Semiconductor, you know, all those chip companies, so they could automate the production of the data that goes into the data sheets. And that little computer could hook up to printers where they'd print the graphs.
Yeah.
You know, and they'd measure like 200 devices and take the averages of them all to generate the waveform and to give, you know, analyze the distribution of results to put in the tables you see in the chip data sheets now. So if I were measuring an op amp, I'd really want a system like that would help me easily document the characterization of the new device, and I could put that all into the data sheet.
There's one other trick that I wanted to show you that this Agilent can do. If you're comparing the two and you're like, what, you know, why would you pay more to get one of those? What can it do? And that's part of what I wanted to learn. It's like, and so I'll basically, let's see, I'm going to make it load an ARB. So both of these instruments can like Ben was saying, you can put in, basically give it a CSV file, you know, and it'll load in your data points and then play them back for you. Let's see if I can recall. So I'm gonna basically make it load an ARB that I put in before.
And an ARB is that arbitrary chunk of data.
Okay, so then let me go back to my scope again. Let's see if I can remember the settings. Okay, and let me turn off the Rigol and turn on this guy. Make him a little bigger and change the thing. Let's change the.
Oh, yes.
Do you recognize this? Let's see if I can get a trigger on it.
Well, can you use your TV triggering to trigger on it?
Well, I'll show you that in a second. Let's see. Oh, there we go.
There we go.
That's triggering. So you might recognize what this is.
Yeah, it's a TV pattern.
Yeah. And so let me take the signal. I have a TV here. I was amazed that it does this. Let's see. Okay. I don't know if you guys can see that.
Yep.
Yeah.
Here it comes.
Warming up. So when I've messed with like the ARB on the Rigol, I don't think it. I've actually tried to do this same signal in the Rigol, and it just can't go fast enough. And it looks kind of the output of its ARB looks like it's doing like sample and hold. For you get stair steps out of it, which is okay. The Agilent has that capability of doing sample and hold, but it also has these filters that make your waveforms look nice and smooth. So like if you look at the color burst on that signal, it looks like a waveform, even though it's like it's like close to the Nyquist criterion, right? It's just barely enough to like make that waveform. But when you look at it on the scope, if you zoom in on it, it looks like a regular TV signal, and it's enough to convince the TV that,
So tell us what you did there, though. Jump back to the beginning.
Yeah.
How did you generate where did you get that? And that's an NTSC test pattern that you're showing there, SMTP.
Yes. So I have an NTSC generator. You might have one as well, Bill. We've had them on the show before. you can grab yours or I can grab mine. Yes. So I had that and I made it generate some color bars. And I basically just fed them into this scope here and just had it capture a waveform, and I had it do 1,000,000 points to get enough. And that's what I was surprised. Like you could actually pull all this off. You could get enough points. And when I first did it, I'm like, I know I needed to get the even and odd, right? Because I remembered that about NTSC. So I grabbed the even and odd, and it actually like showed up on. I have a black and white monitor and it worked. And then I'm like, okay, cool. Let me go put it in the color monitor to see the color bars, and it was in black and white on the color monitor. And then Bill reminded me, like, oh yeah, you actually need 4 fields, I guess they're called, to actually have it reconstruct color properly. So I don't know if you guys can see that,
and make all the math work.
The monitor is really bright, so most of the colors are washed out. But when you first
it started not washed out till the web monitor hit it, but it was a good color bar pattern when he showed it.
I don't know if there's like a exposure. It was like when it was warming up, it looked right for a while there. Yeah.
Yes, it did. Yeah.
I'll turn it off and back on again. Yeah. It's not gonna dang it. But that was the main thing I was surprised is like this AWG can like generate a TV signal.
So what that meant to me was you could have you could create an entire library of everything my signal generator does, and you've eliminated a piece of equipment needed in a lab. Not that we do NTSC these days, but the same thing still holds. You can create a library of signals for your waveform generator.
Absolutely, yeah. And I was just in terms of the technical capability there, it reminded me of like, we had discussed with Charpentier about his work on the VIC chip or whatever, and basically being able to analyze a single line, right, was outside of your reach back in the day.
Right.
And this is, I like this, Frank.
Yeah, I was just about to put that up too.
Throwing out the challenge to you, Mike. Since you're a software guy, you can write a program to generate the NTSC.
Yes.
For a picture. So you get some.
Yeah.
What is it? 480 by 220 or something? Pictures.
252 and a half. Yeah.
And convert them to the NTSC data points and put that into the SIGGEN.
Yeah.
That's a
you
fun
can make
little
an arbitrary
project.
Like a picture to NTSC converter and an arbitrary to just play it. Yeah.
Yeah. There's a lot of.
Yeah.
Yeah, I'm trying to think what other libraries besides NTSC, but that's definitely a cool thing that it can be done with an arbitrary waveform generator, is record and play. Now, how'd you record the signal? How'd you create the initial CBS file?
Oh, so I fed it into this scope and just basically there's a knob I can turn to change the resolution in terms of like I guess you would call it like the memory depth or whatever. How many, every time it displays a waveform, it's capturing that many. So I turned it up to 1,000,000, and then I like put it in what you would call high res mode, because the scope can go faster than that, but it like averages those things together to make like a smoother waveform out of it. And, and then I took it and basically exported it as a CSV out of the scope, and then plugged it in the Agilent. And it takes a while for it to import it. When you plug it in there, I think it's like 10 minutes for it to to like slurp that CSV file in and process it. It's not quick when you have 1,000,000 points.
I can imagine.
Yeah.
Wow.
Yeah, and over 488 is non-synchronous handshaked parallel bus, right? So yeah, someone else says that it's also multi-drop, so you can have multiple talkers and multiple listeners. That's right.
Oh yeah.
That only one can go at a time. So that's the challenge. Yeah, it's not particularly fast.
Very cool.
One question the audience might have is like, do you need like a signal generator like that? I'll offer this. This is what you often only need when you're messing around with a breadboard. This is basically just generates square and sine waves. And come on, that's mostly what you need, right?
Yep.
I think that's how we started. Yeah. That's how we started in the old days. I had a Heath kit with one big knob.
It's got a what's it called, a Wien bridge oscillator inside of there. The old HP ones. Yeah, you turn the knob, and I mean, how often do you really need to generate like an NTSC signal or sweep a square wave? But when you're getting into the stuff, you just need something.
Well, and you know, I've talked about doing ultrasonics and stuff. It's not hard to say, okay, so now create an ultrasonic return for production testing or whatnot. Mm-hmm. So you can have a complicated stimulus and have the test unit under test think it's in real life. You're going, hey, you're looking at a bunch of fish in the water, and it's really just a spreadsheet, you know?
Yeah, Bill, that reminds me, like when you were messing around with the radar and the cantenna stuff, you end up wanting to generate like a triangle wave, so you can like basically.
That's right. That's right.
And that's the difference between these signal generators can't really generate high frequency triangle waves for some reason, but this older one can. This older one can do triangle waves up to 50 megahertz.
Probably because it's doing it with analog circuitry.
Yeah.
And the new ones, they're trying to synthesize everything, and DDS actually has some limitations. Also, someone else said in the chat a bit earlier, it's like DDS will always jitter because, well, I disagree with that, but
within
I'll explain why in a second.
I'll agree within half a clock.
Cheap DDS will always jitter because you have a fixed number of memory cells storing each sample of the generated waveform, and that's just played back like a tape recorder, like a digital voice recorder, right? It's just playing it in a loop. And to change the frequency of what you're just speeding up or slowing down the playback, but there's in a cheap one, there's not going to be any interpolation between points. So you're going to have limitations around the number of samples and the speed at which they're played back. So to get in between frequencies or in between speeds, it's going to skip samples here and there. And that's what is going to give you some additional jitter. But the expensive, well thought out, high quality software, DDS, will use interpolation. So in that scheme, you'll have a digital signal processor running some code with, at the very least, some Hanning or Hamming windows or power law interpolation functions to generate the value between sample points in memory. If you have a certain waveform, it will actually calculate what the point would be if it were to exist at that point.
Okay.
But that takes a lot of extra processing power, and that makes the thing more expensive. So
I've heard...
Eli's correcting me. It's not jitter, it's phase noise. Okay. I'll whatever Eli says goes in my book. So
right. So that reminded me of something, and then I forgot it, which is a clue not to get old in life, because your short-term cache memory just does a constant.
Next time I'm tempted to get old, I'll remember not to.
Don't do it. Don't do it. As somebody that's tried it out, don't do it. It's not worth the. So I can't. So there was something we were talking about phase accumulators with fixed point, and I was thinking of the DDS. So, all right. Any other final words on arbitrary waveform generators, or the trip you took this week playing? Actually, it's been about a week and a half you've been playing with these, Mike. Which one would you buy if you were to buy outright?
Oh yeah, that's a good question. And it's a good question. Like, do you really need to pay more to get like a key site generator? Right. And like, I have not run into a problem where it mattered. Right. Like I've never I don't even know if I've ever needed to sweep a square wave, to be honest, right? Like maybe there's applications where you need that and where this phase noise or jitter comes into play or dithering.
Right.
So
yeah, that's true enough. I've always swept sine waves, when I'm doing sweeps and stuff like that. I'm usually testing a filter or something for its response.
And the Rigol can do that perfectly fine. Like all the stuff we've been talking about is fine on the Rigol. Like when you sweep the sine wave, it's nice and smooth.
Right.
Yeah.
And
so it's like anything in life, right? Like you can get a cheap guitar for $100, or you can get a $5,000 guitar. Like it's marginal differences, right? Yeah.
Right. So one of the other topics we had talked about were test jigs. And it's funny that you mentioned that, Ben, today, because Mike and I have been working on a test jig problem together. And we can't really show it because it belongs to a customer.
Yeah.
But we've been talking about, and some of it's philosophy. What's the philosophy of head of in testing? Where do you test? Who does the testing? In a PCB fabrication process, do you put it onto your assembler house? Do you put it in a final production testing? So that's been kind of on our radar here, and we've been talking about, because processors have processors built in stuff these days. How much self-testing can we do inside the jig before telling the jig, hey, tell the world I'm good or I'm half good or something like that?
Yeah, and it's surprising. A lot can be done, but if you're going to do that, it's just an added expense. I think you have to ask, like, what's in your wheelhouse,
right?
When I was working at Altium for 16 years in various roles, but the most predominant role I had was field applications engineer, right? So I spoke to a lot of people, and a lot of it was interesting that back in the day, and probably still is the case today, there are a lot of very big companies that have huge tool budgets, and they're often using the Rolls-Royce equipment and software. So they have dedicated PCB designers who work with electrical engineers on a team, and all they do all day, every day is lay out boards, and they're using the most expensive software to do it. And then, but what I found a lot was Altium was in those companies, but in the test department, because test engineers, they're engineers, and they have to wear every hat, and they have to develop the test procedures and the test hardware. And so, Altium Designer as a product, one of the things it was attractive for those people was because it was kind of designed from the ground up to work well with the mind of someone who's an engineer who also lays out boards.
Right.
And so it found its way into a lot of test departments, and I got to meet and speak with a lot of like people whose job it was to test. And it's almost always finally handed off to the final assembly and production factory. But someone has to develop the test methods first, because program. If you're doing a mass-produced product, you do not want to to know how to test a product. You basically have to know what's in it and how it works.
Right. So I'd argue that it has to be designed to be testable too. Designed for testability.
Right. Yep. And that's why you have board designers. Excuse me, I just got some goo from this leaky bottle on my fingers. Good PCB designers always take design for test, or DFT, as part of the process. And the CAD tools have, like Altium and other tools, have little wizards for finding and setting test points from component pads. That's all fine. That's really targeted to, there's two stages of test. There's fabrication and then final assembly or in-circuit test. And that also involves microcontroller programming. And I was working on this little project. Again, this is for another company, so I can't really discuss it too much. But I'm having to do a test jig for it. I designed the whole thing with dedicated test points. So I don't like to use the automation in the software for finding and setting test points. It's irritating and doesn't work half the time, because it works perfectly if you know how to use it, but the amount of effort to set up the design rules to get it to work properly is usually kind of time wasting. As a design engineer, I prefer to use components in an actual dedicated library for test. So I have actual pogo pin components, test point components in a library, and I add them to the board where I know I'm going to need them. A lot of people don't do pogo pins anymore, or it's called bed of nails.
Bed of nails, right.
But most of your big factories still, the fastest, most efficient way to test mass-produced products is bed of nails.
Right.
The whole thing can be done by robots. And if it's a small, simple device, you're not going to add all the complexity of JTAG to the whole thing. So
Is it
So
even
bed of
common?
nails, the cool thing about bed of nails, which are basically probe pins that stick up, and you push a PC board onto it, and it picks up all those signals and tests them. The cool thing about a bed of nails jig is it's another PC board that you can
exactly,
make
and
yourself.
that's exactly what I'm designing here. And I'm realizing, like, sometimes if you do this right, and this is why bigger companies have dedicated test engineer teams, it takes almost as much, if not sometimes even more, design time and effort to create the test jig than the actual design that you're testing.
Okay.
Right.
This is a very simple one. And you see, I have this board. I'm designing a jig to test these. I have this outline in a mechanical layer here. Right. And my test point components are designed in the library specifically to have additional mechanical information so that I can take, when I design an actual board with these on them,
Right.
I can then take that and make a copy of that of a certain layer and put that into a new design. And I already have all my snap points for where the test pins need to be placed.
So let me stop you there. Did you just say that you took something from the board you're going to test? You took the coordinates from that and were able to drop it into the coordinates for this, or did you have to manually do that?
No. What I do is I take the actual board design that has the test points on it, and because of the way I've constructed the test point components in the library, I can run a simple query to just select those plus the board outline and just hit Control C, and then I go into my test bed project, which is this one here, and Control V, and they're all in the exact correct location. Right. And then these form the base for soldering the bottom end of the pogo pins. And then I have I need to open this additional project. So let me open project, and I'll show you the other side. So I actually have two board projects for the testing. A lower board. This is the lower board that solders on and connects off to whatever other test hardware or instrumentation I'm connecting to for test. And so the pogo pins, the base of each pogo pin solders to these test point pads, and they point up off the board at right angles from it. But then I have the upper board. I'll just show you what that looks like. And that has a different matching component for the pogo pins. And I do the same thing. I can use automation in the software to locate these exactly at the right place using a spreadsheet. Basically, I can copy the XY locations and names and signal names of all my test points out of the PCB into Excel or Google Sheets.
Right.
And then I can open a new board and copy that out of there and paste them as new components in here. And then I get this, right? So this is the upper board. And those are going to be.
Did you get that out of the pick and place file? Where did you get those locations?
Straight from the actual original design. The board design where I placed the test points, I basically copy those and paste them into the test baseboard, but change the layer.
Right.
Right. And then this board, I did the same thing again, but I can copy the locations out of the list panel in Altium.
That's the question I was asking.
And then paste into a spreadsheet, and I've got all my XY locations, and then I can paste these components into the top board. So the bottom of each of these test pins solders to that baseboard that I showed you before. This board is mounted with, brass standoffs and M3 screws, and then I can solder the sleeve of the pogo pin into these holes. And these boards, I can just mill them all on my other mill, or any desktop milling machine you do for milling prototypes. I will just mill these because I'm only going to make one, so I'm not going to if I needed to make a few test jigs for a very large production run offshore in a factory, I'd have these boards made, or just allow the factory to make this jig, right? Because they can do it cheaper than my own time to do this. But yeah, that's the goal. And then above this, I have additional standoffs going to a plexiglass plate that I can also mill in the machine that is recessed. So it will have holes so that the tips of the pogo pins just poke through the holes. And then it's recessed to take a bare board, or recessed to take a board with the components wherever they're mounted. So I can press that down into its recess in the plexiglass, hit a button, and it'll run the test and give me the pass fail, right?
Right.
Is it common to like have boards be reworked during assembly, like for the ones that fail? Is that, or do you typically just check out the entire board these days? Or
I would say that depends on the product in the factory and what you've instructed them to do. If your product is valuable enough, and the rework is rare and not difficult, I think it's pretty common for them to actually have a technician there who can diagnose problems further and fix them and have a working product leave the factory, so there's no waste.
Okay.
And a lot of good companies will prefer that anyway, just to not damage the planet further, you know. So
right. And at Commodore, we were dealing in such quantities that to try and stick your finger into the process meant everything, the back pressure of, everything would get wet, is the way I'd talk about it, like a fire hose. So the trick was to get the scrap out of the process as quick as possible, and then deal with the scrap as scrap, where they would identify, they bin it into easy to fix items, known issues, things like that. But for us, it was getting it out of the process as quick as possible.
So this is a simple custom bed of nails jig, and you can see a lot of people would avoid this like the plague. I like this process. I think it's very flexible, but yeah, it costs because I have to spend time doing this. But I also know how to use my design tools well enough that I can do this very efficiently, probably more efficiently than most people. But yeah, it's not the fabricator that will do this. It's typically your assembler, and they will this is why the CAD tools, you generate a test point report, and it gives them all the XY locations of test points. But for them to do in-circuit testing, you have to have a pretty good business relationship with them to where you're happy to give them your schematics and tell them.
Mature product.
Like for this product, I actually wrote a test specification and handed it over as part of the production package to the final assembly factory offshore. And it's like, this is how you need to test this product, and these are the specifications I'm laying out for the signal values and voltage levels and all that. But it's very time consuming. You could design a very simple product and spend 4 times that amount of time designing the actual test procedure for it.
All right.
And that's why electronics for aircraft are expensive. It's not because the actual chips used in it or the boards used in it are particularly fancy. They're not. In fact, they're usually 10 years out of date.
Right.
And that's for this same reason. It's because it costs. I spoke to an electronics engineer who was doing VHDL for aircraft systems, safety critical aircraft systems, and so they had to be DO 254 certified. And I asked this engineer, what is the cost if you have to go and make a change to the code to
right.
And he's like, oh, we actually audit that. At the moment, it's $10,000 per line of HDL.
Wow.
To make a change because of the certification costs. So they get something working once and get it working right and reuse it as much as possible.
Right.
Yeah.
So I wanted to show kind of a cheaper version than of doing your own board, but still using pogo pins. And I got this from Adafruit. Let me see if I can even show a close-up of this.
I'm going to show you another way that this has been done in the past too, which I don't like. But no, you go first, and then I'll show you.
All right. So what I've got here is, let me solo. This has the pins on it that are compressible that we've been calling pogo pins.
Okay. I really like those. Those are really cool, those gadgets.
Yes. And so now all you have to do is bring out enough information to the edge of the board that you can clip that onto the edge of the board. And you can get these from Adafruit. She's got a whole selection of these and pogo pins themselves. And if you look through her collection of YouTube videos, she talked about, this is Adafruit I'm talking about, testing each and every of those small units that they produce. They have some kind of little bed of nails or clamp on or some way to test those. So even the small things, to Ben's point, something that costs $0.25 to produce costs another $0.25 to test. So what do you have there, Ben?
This is an Altium Nanoboard 3000.
Oh, wow.
And Dave Jones, this is back when Dave Jones from
Dave did that?
blog. Recently, I got to have a chat with him on the Amp Hour a few months ago now, actually. I forget the episode number, but we had a great laugh because there was some crazy stuff going on back then. But we had honestly, we had some of the best hardware design engineers in the world working at Altium at the time, and they're all just really clever people. This board was cost engineered. This is an FPGA development board with really decent sizes of FPGA and memory for its time. I'm talking 2009 this was released, so it's pretty old now. But at the time, anything equivalent to this was thousands of dollars. And they cost engineered this whole design and got it under $400 US.
Wow.
So these actually, Altium kept being accused and ridiculed by its PCB design purist customers for doing FPGA stuff and saying, you know, all our maintenance dollars are going to your FPGA and embedded stuff. They eventually won that fight because Altium cut that out of the tool. But these actually sold like hotcakes. A lot of people did want them. So it wasn't just a waste of effort and money. These were produced in bulk in a factory in Shanghai that I visited and toured. And it's funny, one of our applications engineers made a custom test jig for this and flew it over to Shanghai to the factory. So this is one of those designs where it tested itself with its own firmware.
Right.
And to report to the factory workers whether something had failed or not. And it could actually report what had failed, exactly which part of the board wasn't working.
Nice.
Right? And all of that was done through this PCIe style. This is a PCIe card edge footprint from the PCIe library. But of course, this whole board isn't PCIe, and this is not pinned out as PCIe. It's just called an ATE or auxiliary test something or other. I forget what ATE stood for. So, but so this was super, super clever. And so every board would come fresh out of the final assembly, come fresh out of the reflow oven, and it would plop into a tray, and it was one of them automated trays. So the next board would come in and it would plop down, and the next board come in and it would plop down. And then the other side of that tray, this would come out and plop into the test jig that was handmade by Altium staff with the PCIe edge socket in it.
Right.
And there was this big metal handle that would push, and it would shove the whole board into the socket.
Right.
It would automatically run the test, generate a report.
Yeah. And
then it would pass. Push the lever back down, it would pull it out of the socket, and then this could get put into. Then that same factory would package the whole thing up into this beautiful box packaging and everything, and then it would ship straight from there to the customer who ordered it. And so that saved a lot of time in production and was one of the keys to getting this under $400. So it's worth putting in the effort if you're going to make a lot. And Altium sold, I want to say, close to 5,000 of these, which you wouldn't expect for a PCB CAD software company selling FPGA development boards. You'd think, oh, maybe they'll sell 100. No, they did production runs in the thousands, and they did several runs before the demand for this board dropped off.
Right.
And then Nick Martin, the founder of the company, got cut off, unfortunately, by the well, that's a whole other political thing I don't want to get into. But this project is the reason why things like part search got into the software, because the engineers employed at the company using the company's own software ran into issues, and they'd go talk directly to the developers and say, hey, we need a way to actually find which parts are actually going to be in stock.
Dog food and stuff.
The one, so this is very clever and was a cost-saving thing. The one thing about this that is a big downside is you have to take all these critical signals from all throughout this board. This is a 6-layer PCB, and route them to this one connector.
A spot. Yes.
So that makes the board layout much more complicated, and it also limits what you can do signal integrity wise.
Right, due to stubs going to those edge connectors, which are terminated the rest of the time.
Exactly. And so the design spec for this was not to be high speed; it was to be decent computing power, and so that's why you have SD-RAM and SRAM right next to the main FPGA on their own dedicated bus. But apart from that, everything else pretty much goes to this connector, and is not impedance controlled, is not high speed. The whole thing was designed to be an industrial platform, right? But yeah, that was kind of fun to see how all that went, and a lot of engineering effort went into just figuring out how do we test this thing. And then they had dedicated firmware engineers developing the FPGA firmware, also baking in the test procedures into that to test the whole thing. But yeah, super. So you can. This is taking it to the extreme, but
right, very cool. Well, it's after the hour here, and that was a good summary. We went all the way from clips to built-in ATE connectors and everything in between. Or not everything in between. That's the two edges of it. But we could talk more about testing at some other point.
Yeah.
So, anything in closing? This was very cool. And Mike, thank you for joining and bringing your Rigolness and your agilentness with
Thanks for having me on. It's fun. Yeah.
Well, I want you to come back, Mike, and show us how you got started with the 488 stuff, because that's super fascinating to me. I've never done it. I think there's probably other people who will watch who will actually be inspired by that. I also wanted to just show this comment as well. That was not the only, no, it wasn't that one, but I'll answer that since I showed it. How do you solder those really, really tiny? They're actually not that small. The ones I'm using are not very small. I can easily hand solder them with a regular iron tip. This was the one. So I mentioned JTAG, and I agree. JTAG was invented to remove bed of nails. That's true.
Right.
And it ended up being used for microprocessors firmware debug and programming of chips more than anything. And that's true. And but you can, like various logic manufacturers like TI have a whole range of 7.4 series chips that are just JTAG interfaces. So if you want to use JTAG for automated tests, you can. And there's JTAG software companies like XJTAG, JTAG Technologies, and they have plugins for CAD tools like Altium as well, where it's like you can use their software to generate your test point report, but instead of creating test points for where to put pins in a bed of nails, it's generating a header file basically for their software to say how to, or to make sure it's like running a design rule check to make sure you've got some kind of access to that node via
Right.
JTAG, so that when you plug in their software, you can test it. So it is still used, but yeah.
So, and that
Anyway.
might be useful too. You combine it with the technique like this, where you can clamp on a board and at least talk JTAG and then unclamp it.
Yeah, yeah.
So useful for small things too.
Well, there's something like that I saw as well that was really good for that some years ago, called the plug of nails instead of bed of nails.
Right.
What was it called?
Well, doesn't Sager do stuff like that?
Well, they do the interface hardware. Let me see if I can find this plug of nails. The company is it's Tag Connect. Tag Connect.
Okay.
Yeah, so I'll just share this really quick.
I have one here.
Oh yeah, so you've got one. Yeah, so they make those. So it's like a JTAG cable.
Hold it still, Mike. Let me solo.
Yeah, so instead of a regular header at the end, it's got some steel centering pins to keep it controlled, and the rest is just pogos.
Yeah.
So you can get one that clips into the board, or one that you just press in and hold it while you click and run your test, and you're holding it there under your hand pressure, and then it does it real quick, and then you can pull it up and go to the next board. So they're super useful as well.
Cool.
It's a lot like that Adafruit one.
Right. Excellent.
Yeah, it plugs into here on our board. This is when we work on at work. There's the thing that Ben was describing.
Yeah,
that plugs in.
Yeah, it's just, and they have this library you can download from the Tag Connect website. They have CAD libraries for footprints for all of their different plugs as well.
Show that again, Mike, real quick.
Oh, sure. Yeah.
Let's go.
This is one
screen.
that we.
Yep,
Get
you
it
can see the
focused.
little. Yeah, it looks
It's
like a
right
connector,
here.
but they're just pads. Yeah.
Yeah, and
Little
there's no
fingers.
solder on them. They're just surface mount.
Mhm.
Yeah, and it reduces the amount of space you need on the board as well for the like
All
instead
the-
of having a whole big box header for programming, you've
Right.
got this smaller footprint. Yeah.
Right. Yeah, I think Mike was saying it's a pain in the tail to hold it in, but it's still.
Oh,
It's,
there's another set of things, like there's clips, and then there's another weird thing, like
Toggle.
they're like 3 tubes that you shove the pins through, and then it kind of sticks into those tubes, and it holds it from the other side. It's hard to describe.
Oh, right,
yeah.
like a friction hold.
I've got one of those here.
Yeah.
Let's see if I can hold this thing up. It's like a little tiny.
Yeah.
It
It just
tubes
adds.
I'm talking about.
It's like a friction hold for the centering pin.
Yes. This goes in, and it's on the other side of the board, and
It
holds
clamps.
it.
Yeah.
And it loses this friction after a while, but yeah.
yeah, right.
It needs to work. Yeah.
Program it fast.
Yeah.
Excellent.
Very cool stuff. Wow. We blew through that hour.
Yes, we did.
I said we're up
Very
to
fun,
nearly an
yeah.
hour and a quarter. Thank you,
Time
everyone,
flies,
for
yeah.
joining us. Thank you, Mike. It's been
Yeah.
really fun
Thank you,
today. I
Mike.
appreciate it.
And good seeing you again, Ben. And
you
I
too.
love your play toy there you had. That was very cool.
Yeah, we'll take a look at that on the show next week, everyone. If you're only just if you missed it at the beginning, I have a toy I've borrowed. I didn't steal. It was actually legally and legitimately lent to me by Keysight. They're wonderful, well-organized people at Keysight, and they sent me an absolute Rolls Royce of an oscilloscope. But I only have it for 2 weeks, so we'll play with that on the show next week, and I'll learn what I can in the intervening time, and we'll give you a tour.
Very cool. Very cool. Excellent. Well, we'll see everybody here maybe next week. I haven't checked the calendar, but it sounds like we'll try and do something next week since we have limited time with the scope.
Yeah.
And otherwise, I'll tell everybody to have a good weekend and be careful.
Yes. And I'm glad you're well again, Bill.
Yeah.
Be safe,
Thank you.
everyone.
Thank you. Everybody have a good day.
See ya.